sulfur is not really unusual. In certain senses, you know, rather it's oxygen that's more unusual. You know, because sulfur, selenium, and tellurium behave very similarly in Lewis structures, whereas oxygen behaves differently. Yeah. And so oxygen is the one that is a little bit more unusual than sulfur. But unusual in the sense that the type of bonding that can occur. For example, oxygen, you know, we have, are there any polyatomic ions that are centered around oxygen? No, but around sulfur we do. You know, we have SO3 2 minus, we have SO4 2 minus. And so oxygen, when we think about oxygen, oxygen can bond 2 single bonds, or it can bond a double bond, or it could bond 3 bonds actually. Let's say a double and a single with 1 lone pair, or 3 single bonds like this. These bottom 2 aren't as stable. Do you know why? The bottom 2 aren't as stable because of the positive formal charge. These ones have a 0 formal charge here. Whereas sulfur has more bonding possibilities. For example, sulfur, like oxygen, can bond 2 single bonds like this, just like oxygen. Or it can bond 1 double bond like this. But yeah, what can happen is it can bond 3 without much trouble, and it can actually bond 4, which you wouldn't see on oxygen here. Because if it bonds 4, what is its formal charge here?
+2.
Yeah, +2. And you wouldn't see oxygen having a +2 formal charge. Do you know why? You wouldn't see oxygen having a +2 formal charge because, compared to sulfur, you know, you would expect it more for sulfur than oxygen because it has to do with the size.
Sorry, the electrons are
You could see sulfur potentially in the +1 oxidation state, 1, 2, 3, 4, 5, in the +1 oxidation state, and possibly even in the +2 oxidation state, because compared to oxygen, oxygen you would not see in the +2. This is +2. You see it, oxygen in the +1 oxidation state in hydronium, other species. But oxygen doesn't do whereas sulfur could potentially go on the +2. And the difference between oxygen and sulfur, the size. Sulfur is a lot bigger, so it's easier to pluck 2 electrons off. It's much more difficult to take 2 electrons off oxygen. Whereas tellurium, you know, and selenium, you know, selenium's even bigger than sulfur, which means it should be even easier, so it's not so unusual. Tellurium, excuse me. So sulfur, selenium, and tellurium are similar, you know, whereas oxygen's a little different because it's smaller. And so sulfur is not really unusual in that family. You know. Oxygen is a little bit, and we're going to talk about that today, actually. All right, any other questions? I have an announcement, though. For Monday, I have an appointment that I couldn't reschedule earlier, so I have to go to that, and then I'll be here by 9:50. So it's a late start on Monday. Probably I'll get here at 9:45 or something. Anyway, let's go back to our structures, and we're going to take a look at building some of these structures. So, what types of structures are you going to build? Well, for molecular ones, we want to build the linear, right? We want to build the bent. What structures have we gotten so far? The bent,
We got
trigonal planar,
and tetrahedron and pyramidal.
yeah, tetrahedral. All right, we have two bent ones. Okay, tetrahedral is going to have trigonal pyramidal here and bent. But these two bents are different. This is bent at 120, the one that's based on trigonal planar. This one's bent at 109, roughly. I know it's 109.5, so we should round it to 110, but it's already rounded, so we'd be doing two roundouts. It's more like 109.4. Shorter?
Yeah.
The angle, yes. In fact, the angle should be less than 109. More like 105 degrees here. All right, so let's build some examples of trigonal planar. Trigonal planar, you're going to use brown. Oh.
What's that?
The brown is the center.
But what is brown?
Hmm?
Element.
What element is brown? Like boron,
That's like
or lots of many different elements. Okay, find the three holes that are 120 apart from each other. So yeah, there should be on the brown there should be three holes 120 apart from each other. Yes, and then plug in long sticks into those. Yes.
It's so much fun.
All right, and then get three of the small white balls and put those on there. Okay, that would be something like BH3, right? The whites are hydrogen. Although BH3 is a tricky molecule. Is it flat?
No. Wait. Yes.
It's supposed to be flat as a pancake, right? You guys have flat? Right. All right. Are the atoms attached by sticks in real life?
No.
No. And so what they do is they move the atoms apart because the atoms actually touch. When we're doing this, we got the atom in the center, and then hydrogens aren't so big. And so we have a hydrogen attached here, a hydrogen attached here, and a hydrogen attached here. And so the actual molecule is something like this instead. This is called a space filling. Again, there's no hard walls on the molecule, but it is. But sometimes it's a lot easier to see if we just separate out the atoms using sticks. And we come up with a ball and stick to show the shape a lot clearer. But you can see it's 120. It's 120 to minimize what? Why does it adopt this shape? Repulsion, exactly. All right. So if you remove one of the long sticks and replace it with a short stick. Go check out model kits for you latecomers.
Would that be a dolba?
No, that would be a lone pair. Why am I asking you to use a short stick? Don't put a ball on it, just a short stick alone. Why am I asking you to put a short stick there? Because, right, what about the electron? A lone pair, why am I representing that with a short stick rather than a long stick? Huh? Okay, because it's not being pulled towards another atom. So if you look at the bonding pair, you know, that pair of electrons is being pulled towards the brown and the white. But a lone pair is only being pulled towards the brown, and that means it's going to be more concentrated or less concentrated on the brown atom. More concentrated. So if you have more concentrated electron cloud, which is more concentrated negative charge density, you're going to have greater repulsions. And so that's going to tweak the angle a little bit. And so the angle is between the white, brown, white. You know, we don't do an angle between the short stick, brown, white. So there's only one angle here, and that angle should be about, it should be about 120, but it's going to be distorted a little bit because of the greater repulsion, so it's going to be less than 120. Okay. This would be an example of BF2 minus, you know, the ion we talked about yesterday. All right, let's move on. Grab either a black or a blue. And then put four long sticks. Okay, that you want to get some practice drawing. So what you want to do is you have to get good at drawing a tetrahedral arrangement of bonds or whatever else on paper. And so what you want to do is you want to align it so that one stick is in the plane here, maybe the stick that goes up, and one stick goes down like this. And then we have one that comes out, and one that goes into the back, right? So can you arrange it like this on your paper and then draw it? Practice drawing it and then trying to visualize the drawing in 3 dimensions. And so what you need to do is you need to put 3 atoms in the plane of the page. You know, the white, the central white, or whatever you use. It doesn't matter. Put 3 atoms in the plane, and then one atom sticks out, the other sticks in.
Can you put dash on the other side too?
You could if you rotate this, you know.
If you rotate this.
Yeah. Switch back.
I guess.
Are you guys seeing this drawing here? Make sure you draw it exactly like this, or make sure it's accurate. Take a look at the book's drawing. Do not draw it like the book. People don't draw it like the book. What? No, the book. I don't know. Oh, finally it's loaded. You want to see how the book draws it?
Yeah.
This is so relaxing.
This is so.
This is methane, right?
Yeah, this would be like methane.
So which one is yours?
So which one is
That
What's blue?
what's blue?
Let's see. There's something wrong with our
Sulfur, right?
network.
Blue
So
sulfur.
slow.
Yellow is sulfur. What is blue?
Don't know.
Cold, man. I don't remember the cold.
Do you have
Blue atom. This is oh, what am I doing? I think it's fluorine. So fluorine and 4 hydrogens.
Yellow is small.
Well, this is incredibly slow.
But is it a particular?
It's a standard orientation for tetrahedral.
It's ugly.
Why is it called tetrahedral?
S4.
It's not because it has 4 vertices. If you connect all the vertices like this,
4 angles?
you make a 4-sided polygon.
Isn't it because it has 4 angles?
No, it has 4 faces.
Faces.
And so it's a 4-face polygon, which is a tetrahedron. And so do not draw it like this. Okay? Don't draw it like this.
What is
Never
that?
seen a
It looks like balloons connected.
It is balloon. This is the balloon analogy. Do not draw it like this, please. Do not draw it like this.
Like a triangle? A pyramid?
Okay. Yeah.
That's weird. Oh, there we go.
Yeah, do not draw it like this. Draw it like this. This is okay. Always draw it like this. Do not draw it like those. Except, you know, all I did was I flipped mine 180. This way. The reason I flipped it 180 is so we can write it left to right in case the structure gets longer. This one's a bit more of a pain
Yeah, I don't like
to write for bigger structures like ethane and whatever else. I'm not sure if I'm going to make you do drawings, but sometimes I do, and students complain because they draw like these up here, and they say this is how the book did it. But I'd like you to draw more like this. But, you know, we're going to draw it differently than what they did. And so let's take a look at our drawing. So what you just built is something like methane. You know, methane, if we look at it, is going to have a structure like this. Right? And what are the angles?
Less than
109.1.
Not less than 109.9, exactly. 109.5, or close, you know. There should be no distortion. You know, tetrahedron is called spherically symmetric. Why?
Because it can.
Symmetry.
It's
Yeah,
like being in
yeah,
some
it's
ball and
this is the same in all dimensions.
all dimensions.
Yeah, it's like a ball.
Like a ball.
What if you take a white ball and replace it with a green ball?
Green?
Yeah.
Green is.
If you take a white ball and replace it with a green, well, the first thing is, let me talk about methane for a little bit. Is methane polar or non-polar? Non-polar. Why?
Symmetry.
Yeah, it's spherically symmetric, so all the bond dipoles would cancel each other out. But there's something you have to know about hydrocarbons. Whenever we have a hydrocarbon, no matter if it's symmetric or asymmetric, it's going to be nonpolar. And so why would an asymmetric one be nonpolar? The reason is because the bond dipoles are so tiny, they're negligible. It's almost a tie between hydrogen and carbon. You know, carbon's just a hair stronger. But these bond dipoles are so small, it's not a big deal. And so even if it were an asymmetric hydrocarbon, any hydrocarbon will be nonpolar. Like oils. Oils are hydrocarbons. It's nonpolar. Whereas this one is very polar. This is ammonia. See, I said black or blue. Black is for carbon, blue is for nitrogen, so it doesn't really matter which one we use. But our drawing is going to be like this. We put the 3 in the plane. One up like this, one across, one down and out, one down and in to the left. And so ours is flipped 180. Do you see it? From this. Except one of these is a lone pair. So remove that. We're going to put the lone pair. This lone pair is going to be in the plane. And that leaves the hydrogens here. And so this is a trigonal pyramidal. You could build that. You could just put a short stick in place of one. And what's that short stick going to do to the other 3?
It's going to push.
It's going to push them in, right?
Yeah.
Push them down, which is going to make this bond less than
109.
109. It's about 107. It's about a 2-degree distortion lone pair per lone
Can
pair.
we say less than 109.5?
Yeah.
Yes, you could say that. Now, if you replace the hydrogen, let's say we took the hydrogen off here and put a fluorine instead, how is that going to screw up the angles? Because fluorine is a different size atom than hydrogen, right? Fluorine's a bit bigger. Since this is bigger, is that going to push down? You know, a bigger atom, will it push down the others? Not really, because it's still a single bond. And so what we're looking at when we're looking at the repulsions is a single bond versus a single bond, you know? Not what the atom is, necessarily. And so this is still going to be about 109.5. It'll be slightly distorted because of the fluorine. All right, over here it's less than, and can you draw ammonia like this?
Yes.
The way we draw ammonia is not like this. Here, the way we draw ammonia is one lone pair in the plane, one bond in the plane, one bond sticking out of the plane, one bond sticking in, like this. Do you see it?
Why would you draw not like the group, or you switch like 180 degrees?
Why did I switch it 180 degrees?
It's the same thing anyway.
It's the same thing, but the reason I switched it at 180 degrees is this. How would you draw ethane? Ethane. How you draw ethane is, you know, this is carbon here. You have to add another carbon, right, in the chain. And the easiest way is just start off here and work left to right. You know, otherwise, if you start off here, we have to work right to left. And so you have to start on the right side of your page to draw longer structures rather than on the left side of your page. And so the reason is if I start adding more and more carbon atoms, then the structure is going to get longer. Another carbon, another carbon. They zigzag like this because we're going to add...
Do you have to connect another carbon to another single bond? Well, not on the dash, not on the wedge?
We could attach it here, but then where do the other... You got to start doing all these crazy wedges, right?
You want to keep it like...
You want to keep... What we want to do, actually build this for me. Let's build ethane. I want you to build ethane. How do you build ethane? You put two carbons together, two black ones. And then fill it the rest. It's C2H6 is ethane. Fill the rest of the position. All right, now you notice you can twist. Can you twist? You can twist the two carbons, right? That's called rotation. Free rotation's allowed. Free rotation about the bond is allowed. You know, it's part of kinetic energy. But what we want to do is we want to stop the rotation because we want to freeze the molecule. You know, because the molecule's vibrating, it's rotating, it's doing a whole bunch of stuff, right?
Yeah.
And so we want to freeze it so it's easy to draw. And so what you want to do is you want to flatten it and get as many atoms in the plane of the page as possible. Right? And so what we're going to do is we're going to put the two carbons in the plane. And then what I want you to do is I want you to twist the other hydrogen. Do you see how this hydrogen's pointed up and in the plane? I want you to twist the other hydrogen so it's in the plane like this, but it points down. And then we finish the drawing like that. Do you see it? And so this is what we do. When we draw these structures, we want to put in as many atoms in the plane as possible. Otherwise, we have to start drawing lots of wedges out. If we bring this one out, then it's just coming out at us. And so every bond is going to come out of the page, right? And so it's not not a good thing to do. All right, now let's build. What comes after ethane?
Methane.
Propane. And so add another carbon. When you add another carbon, twist all the bonds to get as many of them in the plane as possible. Twist as many bonds. Okay, now watch why I draw it left to right rather than right to left. Ready? What I'm going to do is I'm going to put the carbon in the plane. In fact, I want all 3 carbons to be in the plane, right? And so it's going to go like this. Carbon in the plane, and then I could either go up or down. I'll go up. Another carbon in the plane, and I want to put the 3rd carbon in the plane like this. Then I want to put as many hydrogens in the plane as possible. And so it turns out this one I'll put down like this. This one's going to pop out. This one's going to pop in. Over here, one pops out. One pops in. And over here, I'm going to put, maybe I'll just have it superimposed like this. One going down, popping out like that. Do you see? So what's in the plane? What's in the plane is, this is what we are aware of. This What's in the plane? Do you see these atoms here lie in the plane? They're flat in the page. You guys see that? And that makes your life easier for drawing these. Like this.
The hydrogen atom, is it pointing
Okay,
downwards?
this one I didn't draw it correctly, because I didn't start. This is how I would have started this. I wouldn't draw it like this, right? How would I draw it? Actually, I shouldn't have drawn it like this. How would I have drawn it? I would have drawn it like this. I start off with these 2 in the plane. This is my standard start point, like this, right? That means one comes out and then one goes in. And then I attach a carbon here. And then I'll flip this like this. So this, actually, no, I don't want to flip it. I'm going to twist it like this. If I twist it like this, I'll get these 2 in the plane, and that means one comes out and then one goes in. See that? And then I'm going to twist this bond here so this one goes in the plane, and that means one comes out like this and one goes in. Like that. Do you see it?
Like this?
Yeah, something like that. And then I can keep going. Add another carbon, add another carbon, add another carbon, and then do you see I get the zigzag line of carbons? All flat in the plane of the board. So what would this be?
3 carbons?
No, 1, 2, 3, 4, 5, 6, 7 carbons.
That would be
Heptane. All right, so do you see why I start off with this arrangement rather than this arrangement here? It's because drawing the more complicated ones is easier. If you only drew methane, then no big deal. Doesn't matter which one you use.
Question.
Uh-huh.
As you go connect more carbons, like I get confused like which side to put dashing wedges. Like for example, for the second carbon, if you switch like dashing wedges,
Just make it. Make the structure and then look at it.
if
Oh.
you flip it, and then it's the correct structure.
if you flip it like this,
If you
yeah,
flip
that's
the
okay.
dashes,
It's okay because they were actually superimposed on each other. It depends on what angle you twist it at. If you look at it down this way, then it's going to look like this. If you look at it this way, it has the opposite.
Either way is fine.
Either way is okay. But don't mix them. You know, if you start with one pattern, you're looking at it like this, then you better stick with it. Right? Don't start flip-flopping.
Okay.
All right?
So can you do the other carbon, like finish it? So the other one would be, no, go back.
Which one? The last one?
Yeah, can you like the whole sequence? I was trying to do it, but
The whole sequence? Okay.
I
The
get
whole-
confused in the third one, the fourth, that one.
This would match this.
Oh, so it would, oh, okay.
This one matches, do you see? And this would match. Okay, this final one, what I'd probably do is I'd probably just twist it. Actually, no, I'll probably just leave it, this, the hydrogen. I might twist it to match that. And so if I rotated this last one to match the first one, but just opposite, it looks something like this. But you know, I could rotate it so to flip this bond, which is in the plane, flip it down and be it in the plane as well. Okay. All right, let's take a look at this last structure here. Except this is not how I want you to draw water. Oh, did everyone get this? Monday, late start, 9:50 a.m. please. Thanks. If you look at these water, this is what I see. Actually, this is okay. You could draw water like this because this lone pair is in the plane or out of the plane. This lone pair is in the plane, this lone pair is in the plane. In the plane, in the plane, this means this is out of the plane going out and this one's coming in. Do you see it? It's like that. But typically what we're going to do is we're going to draw as many bonds as we can in the plane. And so if we draw as many bonds as we can, then that means we have something like this, and then this lone pair must stick out like this. And so I'm going to draw solid circles and then dash circles showing the lone pair going in. So we have a lone pair coming out at us and a lone pair going in. A lone pair in the plane I draw like this. For ammonia, I would draw there's two circles. So this is the what I use to show the difference. In plane, and this one's, you know, they're out of plane. The angle here is going to be less than 109. It's going to be more like 10, yeah, 105. Okay, are we good with these structures? Let's move on. Well, actually, how about ammonia? Is ammonia polar?
Yep.
Yes. Ammonia is polar. Very polar. There's bond dipoles that point up here, up here, up here. If you sum these bond dipoles over 3 dimensions, we get the molecular dipole. The molecular dipole will just point straight up. How about water? Is water polar?
Yeah.
Yeah, oxygen is more electronegative, so the bond dipoles point in towards oxygen. So the molecular dipole is going to point in this direction. And so we just think of pushing or pulling. if the nitrogen's pulling, there's going to be a net movement up. Here, if the oxygen's pulling, there's going to be a net movement towards the oxygen, electron cloud density. And so we say that this end is delta minus, this end would be delta plus. In fact, the two hydrogens are delta plus. This end would be delta minus, this end would be delta plus. So we get a charge separation. Bond dipoles. Bond dipoles can actually be measured experimentally. All right, this is continuing with the balloon analogy here. This is 4 balloons. Do you see what geometry it adopts? Tetrahedral. But what if we put a 5th balloon? If we put a 5th balloon from underneath here, it's going to push these 3 up. And so the 5th balloon comes in here, pushes these 3 up, and we get this geometry. Have you ever seen this geometry before? No. This geometry is called trigonal bipyramidal. Trigonal bipyramidal, we have a trigonal planar arrangement of balloons here, just this flat triangle. And then we have one balloon straight up and one balloon straight down. And so they call it trigonal bipyramidal because you form 2 pyramids here with a triangular base that are inverted on top of each other. If we add a 6th balloon, where would the 6th balloon go? You probably want to squeeze it in here. If we squeeze it between these balloons, what it's going to do is it's going to push these 3 out. And that's what happens here. These 3 get pushed out. This one should be called a square bipyramidal. Do you see? Because it looks like a bipyramid with a square base. We have a square plane. This is called square planar arrangement of balloons here, and then we got the axis here, one pointing straight up, one pointing straight down, and then if we look at it like this, we have 2 inverted, or a pyramid on top of a pyramid, inverted pyramid. And so these are 2 new geometries, probably. This one again is called trigonal bipyramidal. This one could be called square bipyramidal, but it's not. It's called octahedral. It's called octahedral because when you connect all the, when you make these pyramids, you'll count 8 faces on the pyramid with the 6 vertices. Octahedral, like tetrahedral, has spherical symmetry. It's isotropic. Spherical symmetry. This one is not isotropic. Even though it kind of looks isotropic and spherical, it's not, because it's not the same in all 3 dimensions. These ones are a little different in the triangle part than these ones here. We call these the axial positions. It's an axis because we can kind of think of it as spinning along here, and it shows symmetry. It's called 3-fold symmetry. Over here, this is the axis. This shows 4-fold symmetry. Each time you rotate it 90, it looks the same. Each time you rotate this one 120, it looks the same. So how do we draw those? Draw them. Well, let's make it first. We can make the trigonal bipyramidal using the brown ball. So use the brown ball. And the way I draw this is, okay, let's position the brown ball here. I want 3 in the plane. And so the 3 that I'm going to make in the plane form a T like this. And that means one sticks out of the plane and one sticks in. So I'm going to put 4 white balls here, or 5, actually 5. And so go ahead and make this and draw it like this. And then I'm going to label them. The one up here is called an axial. This is an axial. This one's an equatorial. This is equatorial. This is equatorial. So we actually have 3 bond angles here. We have the axial-axial angle. So we go axial, center, axial. What's the angle? 180. And then we have the axial to equatorial angle, which would be 90. And then we have the equatorial to equatorial angle, which is 120. And so these are the 3 angles that you should see: 180, 90, and 120. Do you see all 3 of those? So which has more breathing room? The equatorial or the axial? The axial has more space? Okay, this is the way we're going to analyze it. The axial has 3 90-degree repulsions, whereas the equatorial has 2 90s and 2 120s. It turns out that the 120s aren't nearly as strong of a repulsion as the 90. In other words, the 90-degree repulsions are much worse than the 120s. In fact, the 120s, there's plenty of breathing room, and so they aren't that significant. And so what it boils down to is 3 90s versus 2 90-degree repulsions. Which one is it? 2 90s is going to be better than 3 90s. And so, in other words, the equatorial positions have more space, less repulsion. You see, it's not isotropic or symmetric, totally symmetric. So more space, less repulsion. Well, anyway, we can build one. You just build something like PCl5. They're missing one angle here. 180-degree angle, axial to axial. PCl5 is like this. Now, PCl5 is a weird one because this is what we call an expanded octet. Phosphorus has 5 valence electrons. Chlorine has 7. 7 times 5 is, this is 7 times 5, 35. 35 plus 5 is 40 electrons. Is that right?
Yeah.
And so here, when we build this, we need to bond 5 chlorines here. And so maybe we'll start off with something like this, and then we'll complete the octets to all the chlorines. And that completes all the electrons there. Now, the strange thing is, what's going on with phosphorus? Phosphorus is more than an octet. Phosphorus is 10 electrons. And that means the extra electrons, where do they go? They got to go somewhere. They got to go into the next shell. Well, if they go into the next shell, isn't that totally destabilizing?
Not for fun. Is that one of the assumptions?
No, nature, okay, there's a battle right here, right? And I talked about this battle before. You want to maximize the number of bonds or maximize the strength of the bonds, right? At a minimum cost, energy cost. And so we saw this happening with magnesium, what was it? Magnesium oxide? Yeah. Saw that. And so the correct balance was Mg with a 2 plus and O with a 2 minus. Well, the same thing here. What is the cost? The cost is we've completed the octet, and now we're going beyond the octet by 2 electrons. Where do those 2 electrons go? Those 2 electrons have to go in the next shell. Well, if they go in the next shell, isn't that going to cost too much energy? And the answer is maybe, maybe not. For phosphorus, let's take a look. For phosphorus, what do we have? We have 1s2, 2s2, 2p6, right? 3s2, 3p. Now, how many valence electrons does phosphorus normally have?
3. Wait, phosphorus?
5. 1, 2, 3, 4, 5. So this is what's going to happen here. What's going to happen here is the chlorines are going to come in. The chlorines are going to come in here and bond, bond, and bond. Do you see that? And so this is how we fill the octet. Except this is called PCl3. PCl3 looks like this. Phosphorus has a lone pair. Do you see the lone pair? Here. And then it's bonded to 3 chlorines. And so 1 electron comes from phosphorus. The other electron comes from chlorine. That's what makes the bond. And then chlorine's got 3 lone pairs here. And so what we're looking at here is this bond. And the same thing happens here. Phosphorus trichloride is what we call a trigonal pyramidal structure, yeah. Yeah. And so this would be PCl3. PCl3, let's just draw it like we normally draw it. Do we have to show the lone pairs in a 3D on chlorine? No. We'll just show it like this. That's PCl3. So what's happening with PCl5? What's happening with PCl5 is this. What we have going on in these bonds is 1 electron comes from phosphorus, the other electron comes from chlorine. Now let's take a look at the charge. What's the formal charge on phosphorus? Zero. Phosphorus has 5 valence electrons, and it's got 5 electrons. So pretty much phosphorus has retained its valence electron. But what happened to the valence electrons? Do you see a pair of electrons? No. And so what's happening in PCl5 is this. When we look at phosphorus, it's a 1s2, 2s2, 2p6. But when we get to the 3s, this is what's going to happen in the 3p. in order to maximize bonding, we're going to split up the electrons. There was 2 electrons here, but now there's just 1. And we're going to still be singly. And so what happened to this extra electron? This extra electron got promoted into the next shell. Boy, getting promoted into the next shell doesn't sound so favorable, does it? So this is going to be higher in energy. But we've kind of seen something like this where electron gets promoted. Where did we see that before? An electron got promoted into a higher energy subshell, chromium, right? Well, this is a kind of a similar situation where we're going to promote the electron. Why? Because of the payoff. What's the payoff? We're going to be able to form more bonds. Okay, now in the next shell, what orbitals do we have in the next shell? All of them. Tell me all the orbitals in the next shell. The 4s, the 3d, and then the 4p. Okay, which orbital will that electron get promoted to? You'd think the 4s, why? It's the lowest in energy. But in terms of distance, if you have a 3p electron, here's the nucleus. The 3p electron's here, right? The 4s is way out here, right? Whereas a 3d is right here in that general vicinity, right? Because they all have the same effective distance. And so it turns out that this electron does not go into the 4s. This extra electron goes into the 3d because it's the same n. It's much closer, right? Does that make sense? Yeah. Okay. Now, when chlorine comes in, chlorine can bond like this. Chlorine's going to bond here. Chlorine's going to bond here. Chlorine's going to bond here with an electron, here, and here, which gives us a total of 1, 2, 3, 4, 5 bonds. And so even though this costs energy, we get energy in return from bonding, right? Maximizing the number of bonds. Could we have 6 bonds? No, because we ran out of electrons, right? All right, this is for phosphorus. It turns out other members of the family do the same thing. Arsenic does the same thing. Antimony does the same thing, except for nitrogen. Nitrogen will not do this. And so let's talk about nitrogen next. Here. For example, let's say we wanted to make NCl5. NCl5 would look like this. NCl5, what's the formal charge on nitrogen? Formal charge on nitrogen? 0. Why? Because nitrogen has 5 valence electrons, and it ends up with 5 valence electrons. And then chlorine's going to contribute the other electrons. You see that? And so let's take a look at how we can do this, because normally when we look at nitrogen, let's say NCl3. Okay, so let's take a look at NCl3. NCl3, no problem. NCl3 is going to look like this. Lone pair, Cl here, Cl here, Cl here. Maybe I shouldn't have picked Cl because I got to draw all these lone pairs. Pick NH3. It's all right. Okay, so we have this, and let's take a look. We have the 1s is filled, and then the 2s. 1s is the core. Remember, the core doesn't participate in the bonding. We got the 2s, 2, 2p, 3. So we got 5 valence electrons. valence. And then we can easily see that 3 chlorines are going to come in here. One's going to bond to this orbital, one's going to bond to this orbital, one's going to bond to this orbital. In other words, this is how we create the bond. We create the bond here by nitrogen contributing 1 electron and chlorine contributing 1 electron to form this polar covalent bond. So no problem with this, right? Yeah, no problem with this. NCl3, no problem. PCl3, any problems with PCl3? No. And then PCl5, no problem. You know, PCl5 exists, it's fairly stable. You know, it's got all that bonding makes it quite stable. How about NCl5? NCl5, it's the same situation. We could draw the Lewis structure here, no problem. That's the Lewis structure, right? But let's take a look at what's happening with the orbitals. The 1s orbital is 2, the 2s orbital, the 2p. Now what we got to do is we got to promote, remember, we got to promote this two paired. We'll promote it up to the next shell. If we promote it to the next shell, well, what does the next shell consist of? 3s and 3p. And so in this case, it would have to go to the 3s, which is lower in energy. And so this is this a big jump or a little jump? This is a big jump, yeah. Because when you're at the n equals 2, you're here, 4 times, let's say. But when you go to n equals 3, you're 9 times distant from the nucleus. And so this is too much energy.
So it can't happen?
Yeah, this does not happen. And so the maximum number of bonds is not,
Not possible.
well, anyway, we can't do this. In other words, we cannot expand the octet. This is called an expanded octet because it would have 2, 4, 6, 8, 10 electrons. We cannot expand the octet because it's too hard or too unstable. Here. And so it doesn't work. Cannot expand the octet for nitrogen. And so the end result is this. The end result is for third period and lower. And let's say, what should I say? Lower in the periodic table, but higher in number? Should I say third period and higher, or third period and lower? Well, third period and beyond. Say that. For third period and beyond, empty d orbitals with n same as valence orbitals equals possibility of expanding octet. And so the problem with the second period is this. Problem with nitrogen and second period elements in general there are no 2d orbitals. 2d orbitals are forbidden. Therefore, max is an octet. Max is an octet.
So that's where the exceptions come in, right? Like phosphorus
Yeah.
can have 10 or...
Right. Since we're talking about nitrogen, we can look at another example. We could look at ammonium. You know, ammonium has, it looks like it has an expanded octet, doesn't it? Right? Ammonium has 4 bonds.
So it has 8.
And so when we look at, well, how many valence electrons does nitrogen have? 5. So 1, 2, 3, 4. 1, 2. Oh, valence electrons.
Balance it.
Yeah, 5. 2 core electrons. So it's got 5 valence electrons, but now I have to make 4 bonds. Can I put a hydrogen in here? Hydrogen pops in here?
Nope.
No, what would this violate? No, this doesn't violate Hund's rule. Pauli exclusion principle. No. It's filled. No room. The only place it can go is here, here, and here. Well, how the heck does nitrogen form 4 bonds to hydrogen? Yes. Okay. This is the way. That's one way of thinking about it. This is the other way of thinking about it. The other way of thinking about it is this. How many valence electrons does chlorine have? 7. How many valence electrons does chloride have? 8. 8. And so the number of valence electrons depends on the charge. You know, the higher the positive charge, the fewer the valence electrons. The higher the negative charge, the more the valence electrons, right? And so what we do in this is we got to look at what is the charge on the nitrogen. When I say charge, I'm talking about formal charge. What is the formal charge on nitrogen here? +1. If nitrogen's +1, that means it's lacking 1 valence. It's missing 1 valence electron. And so a nitrogen with a +1 charge only has 4 valence electrons, which means that
You can make another bond.
we can make another bond. And so this is it. This is not neutral nitrogen. This is nitrogen with a plus formal charge. Is that, and so again we see just an octet there, right? What's the shape of this molecule, or this ion?
Tetrahedral.
This is tetrahedral. The problem is on tests I ask, what is the bond angle here? You know how many people tell me the bond angle is 90 degrees? Lots.
It looks like
Lots, because it looks like
90.
90 degrees, but unfortunately Lewis structures aren't always drawn accurately. Right.
So that would be a 109.5?
109.5. Let's take a look at this. Do you recognize this species here?
Yes, that's amide.
That's amide. Okay, why don't you draw the Lewis structure for amide, and then show me what's happening with the valence, or actually, this is both core and valence. Show me what's happening with the orbitals for amide. Draw an accurate 3D drawing of amide.